Okay, in this example where we've got the simply supported beam midspan load, we've already dealt with shear moment diagrams, we've dealt with moment curvature, we come up with slope equations that relate then to us what's happening inside the beam, and we need to go one more step of integration to go from slope to the transverse displacement. So now we want to get that with this little thing V, and so here we go. Our V is going to be the integral of theta dx. Right now we can make that a little bit easier if we multiply by a constant. We did that in our previous step, and that was how we got this sets of expressions here. They do have to get dealt with here separately. The integral of now px squared over 4 plus c1 times dx, and the integral of minus px squared over 4 plus pl over 2 times x plus c2. Wow, this is just, painful to have to work out all this stuff, right? And so you could do this with symbolic manipulators, there's no doubt. They may or may not handle your constants of integration well, so you do have to be careful in how you do all this and how you set it up. But this integral then is going to be px cubed over 12 plus c1x plus another constant, c3 we're now up to. That's the first segment. Right? And then segment 2 we get minus px cubed over 12 plus plx squared over 4 plus c2x plus c4. Oh, golly, we got yet another one associated now with segment 2. But now, note, we've got boundary conditions we can work with, and we have another continuity condition that we can work with. And so the easy one, of course, is a v at 0, and that would be associated with segment 1. So p times 0 cubed over 12. Oh, this needs to be ei times that, right? Ei times that plus c1 times 0 plus c3. That has to be set equal to ei times the value there, which is 0. So the whole thing is 0. That was convenient. And notice that that's nice. c3 is going to be equal to 0. Great. Now, when you go put in v at L into this other one, then you're going to get ei times, minus pl cubed over 12 plus tl times l squared, which would be l cubed, over 4 plus c2 times l plus c4, and that's going to get set equal to ei times 0. Well, we don't get one constant, we get 2 sitting in there. So that's kind of unfortunate. We don't know C1, we don't know C2, and we don't know C4. But we have one more equation left for us that we can write, the continuity condition that says that our segment of N1, the displacement evaluated at the midpoint, has to equal the segment displacement in number 2 also at that midpoint. We have those two equations for those. We can evaluate those at the L over 2, set them equal to each other, and we'll get another expression involving the C2, C3, C1, C2, C4, along with the continuity condition that we have up here between C1 and C2. We can now work through all that, and that's what you get to do yourself. Now, you'll find in the better textbooks that they'll show you this work, so if you want to cheat and find it there, you can, or you can follow the cheater's approach, which is to make some assumptions about what happens at that midpoint. Don't do that, because that's not going to be generally true. You need to know how to do this otherwise. So I'm going to let you do the rest to figure out then what all those constants are, and then once you have that, you can set the derivative equal to 0. You should find that the derivative is equal to 0 at the midpoint, and then once you know that, you can go in and evaluate your beam segments at L over 2 and find your maximum displacement, and the answer should be PL cubed over 48 EI.